title is wrong and I can't fix it because my password manager, I made an oopsie. I need to get to the other computer. It's not this computer. Anyway, so I can't log in to fix it right now. But yes, so, but the good news is it's updated on the screen, so when people get the email and it says the same thing as last month, they're going to be like, oh, he forgot to update it again, and then they're going to come, and then they're going to see that it says Utah Zig August 14th, Niles Salter, Hyper-Optimize the Zig Parser Part 4, and they're going to know what's going on. They're going to know this is the presentation I've been waiting for. For an entire year. Or has it been more than a year? I think it's been more than a year.
I started the original one. It was the beginning of 2024 is when I gave the first thought. Okay. So it's been a while.
Yeah, so anyway, so we are streaming. Just people that are receiving the stream are receiving the wrong title in their email when it starts. And I may not be able to fix it on Twitch, but it's only going to be on Twitch for a few days, so it's all good. Okay, anyway. All right. Hey, yeah, that's great. Yeah, that's wonderful. That's wonderful. Okay, so, Herb Body, thanks for coming out to Utah Zig. I hope that you've enjoyed the friendly banter and nonsense that we've been doing before our wonderful presentation night. We want to thank Vivint for providing the pizza and the space for us, Jeff for being our host, and welcome one and all to Utah's least safe meetup. If you want the most safe meetup, that's Russ. They're right over there. But if you want unsafe, you come here. I'm in Zig. And with that, I'm going to hand it over to Niles to present to us the final presentation. Never to have another presentation again, because he will not learn anything more about this topic. He's completed the learning cycle and is done.
Yep.
The final part of hyper-optimizing the Zig Parser. Niles, take us away.
All right. Well, I do want to start with the basics and a recap. This is from 2 presentations ago, and it already has a good introduction to the topic. So I'm just gonna go through that.
When it went black, I thought the screen share had stopped. I was so scared.
Okay. Are we still going?
Yeah, we're still going.
Okay. All right. So we want to go fast. I've said a bunch of things in the past, and it's listed here. Amazing. So what are we trying to do? We're trying to tokenize again. So we have some source code, and we want to group the words and the multi-character symbols together into one thing. And the reason why we want to do that is because in subsequent phases of either a compiler or in some kind of project your IDE is running every time you type, you want to do some analysis on the code, and it's, let's say, difficult to go one byte at a time when we can group words together instead, and that's kind of an irreducible semantic unit that we call a token. So yeah, as an example, we have export and FN, those become tokens, column counts, that's one word, a token, and yeah, basically any grouping there is a token. Multi-character symbols like the asterisk %, that is also a single token. A token has inside of it a kind, a start, an end, and or a length. We don't have to store all of this data, but fundamentally this is the information that we want when we actually ingest this data later. So our kind is typically going to be a byte, which just, yeah, it's an enum. It tells us what's in it. It can tell us which keyword it is, which operator it is, if it's an identifier, a string, a number, etc. You could also have white space, but usually white space is omitted from a stream of tokens. Okay, so the basic idea of a tokenizer looks like this. Well, what are we doing? Okay, so typically you have a source input. That's just how we denote a string in Zig. You have open and close brackets and a constituate. That means a slice, which is a pointer and a length. And what is it pointing at? It's pointing at U8s that you cannot modify through this, hence the const. So that's what we're talking about. I declare cur, which is just a cursor into the file, and then we have tokens. And this is going to allocate a buffer to hold on my tokens in. Okay, amazing. So we start off with a while loop. We switch on the first character in the file, and let's say the first character is a letter, as is the case underneath the code. You can see it's pointing at the E in export. And yeah, when we see a letter, we're going to go into some inner while loop. And did I skip a section? Oh yeah. So here's the basic tokenizer. Amazing, guys. Okay, the basic tokenizer, I didn't have like a line-by-line step through, I guess, or maybe I took it out. But the basic idea, you switch on the first character, and then let's say you see a letter, you're going to enter this inner while loop, and you're going to keep grabbing successive characters so long as they're in the set of valid continuation characters. And this is a broad pattern that we see for all kinds of things, including white space, or if you see the beginning of a comment, it's going to end once you see a non-new line. And so kind of, let's say the hot loop of a tokenizer is this. We look at the first character of a token, we figure out what category it's in broadly, and then we match the continuation characters. So the problem with this is, one, you're going one token at a time, or one character at a time, I'm sorry, and that can introduce a lot of penalties on top of, you know, the fact that you could have been doing multiple at once. There's also the issue of you can have branch misses on each of these. So this while loop here, for those who don't know, the CPU wants to predict where it's going to go at any given time. And so, you know, it's a multi-stage pipeline. You have an instruction fetcher, decoder, scheduler, and executor, and you have some other things. And at the top of the pipeline, when you see a conditional branch where it says, if some condition is true, we're going to go to code snippet A. If some condition is false, we're going to go to code snippet B. The problem is, when the instruction fetcher and the decoder, when they first see that, it hasn't been computed yet whether the answer is true or false. So where's it going to go? Well, we have a branch predictor unit, which we can use to guess the future based on past history. And branch predictors are very good, but when it comes to a tokenizer, you're asking for an impossible task, because this while loop here, effectively the CPU wants to guess how many times this is going to run before you hit this break right here. And so, you know, if you see a stream of word lengths in a file, you know, if I just say a bunch of numbers like 5, 8, 3, 5, 7, 2, 3, you know, how long is the next identifier? Ultimately, it cannot be predicted. Ultimately, you're asking for the CPU to do something impossible, and it will get it wrong. Unless it memorized the whole file, if it already saw it, which is possible, and very cool. Okay, so a better tokenizer, I already started showing it. Instead of branching on each individual character, you can produce a bit string. And here we produce a bit string that tells us where are the alphabetic, underscore, or numeric characters. And we can use that. We can use a count trailing 0 operation on the not of the bit string in this case. And so the point is that without iterating over each individual character, we can figure out how long the particular token is for like most tokens when it comes to identifiers / numbers / keywords. Those things we can use this exact piece of code for. When it comes to strings, we also have a similar thing. We can jump to the end. When it comes to comments, we can jump to the end of a line. And so this allows us to, typically in one step, jump to the end of a particular token. We might go off the edge. You know, if we jump forward by 64, for example, we might have to loop back around. So there is still a loop, but in practice, it's going to loop around typically 0 or 1 times. So it's significantly less branchy, let's say. So yeah, this just goes through a couple times. Let's say we see the F, we produce the bit string again, and we can use the count trailing 0 to jump to the end of it. And we see a space, we jump over it. We see the C in column counts, we produce the bit string again, and we jump to the end. Amazing. So this might work. Yeah, here you go. Here's what SIMD code looks like at the assembly level. You can see we have frame pointer stuff that we do not want. I actually figured this out recently. When it's behind me, it's hard to type. Okay. Let's do it that way. There you go. So yeah, we load in some memory. We're doing work on 64 bytes at once. We're producing 64-bit bit strings in these K registers, and yeah, it's blazingly fast. So yeah, let's continue. All right. So here it is in a loop. You can see we can extract constants. Amazing. Okay. There's SWAR emulation. I don't want to go over that today, but it's cool. And there's ARM stuff. Okay. I think I'm pretty much done with this one. Oh yeah. The other thing to know is instead of producing the bit string every time, I also improved this particular tokenizer to just reuse bit strings per chunk. And so at the start of every 64-byte chunk that we ingest, we just speculatively produce these 3 bit strings, and then on demand, when we actually need it, yeah, I don't know why there aren't so many lines to jump through here. When we actually need it, then we query it. So let's see. Switch somewhere. Oh, you know what? It's written in such a way where the code always tries to go through this particular line, which is kind of cool. And so yeah, it will just take the selected bitmap out, and it will shift it right by the current misalignment, is what I call it, which is just your position in the particular 64-byte chunk. And you do a not, you do a count trailing 0. You do the same query that we already saw. All right, amazing. I'm going to switch over to my new presentation, I think. Yeah, here's a cool one though. This is a trick we still want to use. This is depicting a VP chef B, which is going to come up. What this does is, I can hear my fan going, playing the animation. So the top and the bottom are depicting the same thing, but the bottom you see ASCII characters, and the top you see the hex representation of them. And so I want to explain what this does before we actually get into the new tokenizer I made. What it does, it looks at the lowest 4 bits of a particular character. So you can see in the hex, that's the second character. And that is the index that we're going to look up. So we have 16 bytes. We're going to look up all of those bytes into a table at once. But we just look at the lowest 4 bits because it's a 16-byte table. If we have a number that's larger than 16, well, we partially ignore it, but actually, if it's larger than 128, it'll return 0. That's just the semantics. All right, let's X out of this. All right, so here's my new tokenizer step by step. The reason why this is better is we want to do more SIMD stuff. This is a slide from my Intro to SIMD presentation. And doing more things in SIMD allows us to increase the amount of work per instruction. And my old tokenizer partially did that by making it so that we're not looking at each individual byte of a file as much as we are looking at each individual token of a file. But we can actually unlock a higher level of parallelism. And the way that we do that is, oh, we're doing something now. Okay, this is a slightly modified slide from my other presentation. Let's say that we have this export fn column counts line of code, and the idea is that we can produce bit strings which tell us where each token starts, and a bit string that tells us where each token ends. And we can line that up with a vector of indices that count from 0 to 63, and we can leverage instructions like a vector compression or a vector compaction to do this pretty sweet animation. So I'll play that one more time. This is the secret sauce right here. This enables us to actually do, like, we can do all of the analysis we want completely in parallel for a 64-byte chunk, or actually we're going to go to 512-byte chunk at once. And the secret sauce is vector compression. This enables us to not go 1 byte at a time and not go 1 token at a time. Instead, we can actually produce all the data we're interested in for all the tokens of a chunk at once using this vector compression. We can use a similar technique where we can place tags, the tag kind values for each token. We can place them at the position corresponding to the start of each token, and we can use the same vector compression technique to isolate it at the end. So I'll open this up to the floor here. What would be the first major obstacle to trying to produce all tokens in parallel when it comes to a programming language construct that changes how things tokenize? So, in this code here, right, I want to figure out where does each identifier start and end. And I can do that very easily by having a bit string of alphanumeric or underscore characters here. And then I can shift to the left by 1, and I can do an and not to produce my starting position of each one. So I'm effectively saying, where do I see a non-alphanumeric underscore followed by an alphanumeric underscore? And then I also ask for the reverse. I say, where do I have an alphanumeric underscore followed by a non-alphanumeric underscore? So what's the first obstacle for this working for a complete programming language?
Will you clarify the obstacle to what?
Yeah, there's a language construct that changes how things tokenize, where if we see a word, we wouldn't want to tokenize it as a word.
If it is a keyword.
If it's a keyword. We can tokenize it as a word or an identifier and reclassify it, so that's fine.
A type?
What actually inhibits being fully parallel in terms of tokenizing the identifiers?
Comments, right?
Comments. Comments,
Oh, yeah.
strings, character literals. We don't want to tokenize things inside of those. So yeah, that's the first thing we have to overcome for that. So yeah, now I have some walkthrough in my code. I start off with a bitster struct where I just have 8 U64s of each of these. And the most recent thing that I've done with this is go to 512 bits, which is 8 times 64. And the reason for that is partially because I want the kind of like basic SIMD acceleration that you get. So I'm going to open up another thing here in a second. But the idea is, when we do bit manipulation stuff, anytime we do an and or an or, we can trivially translate that from a 64-bit instruction to a 512-bit instruction, and it will be roughly the same speed. Actually, a lot of times the throughput is the same as well. So we could do 4 64-bit ands, or we could do 4 512-bit ands. And so trivially, we have a factor of 8 reduction in the number of instructions. We can do a factor of 8 more work per instruction for some of the instructions. But actually, we can do better for some things. There's a VP turn log Q instruction. And this is actually a ternary instruction. So this takes in 3 input operands, as well as a 4th immediate argument, which is an 8-bit immediate. And this 8-bit immediate is a truth table. And so, you can see we have all the possible combinations of 3 bits here. And we just specify the output that we're interested for any combination, or the compiler will specify it for us. But the point is, we can use ternary operations in SIMD. This does not exist in the general purpose instruction set. And so we can actually do, typical case, we can do 16 times more work with this instruction than you would with a regular general purpose and, for example. With this, you could do 512-bit and you could also stuff another thing in it. You could do an or an and not, or XOR or whatever. Any bit parallel operation you can express if it has up to 3 operands across the whole expression, it can be encoded in a single one of these instructions, which is pretty cool. So going to 512-bit can get you some speedups for that reason. It can have some drawbacks as well when you want to do a shift across 64-bit lanes. We don't have an instruction for that, so you have to emulate it with more than one instruction. It ends up being 2 or 3, and yeah, it's not a massive win, but not as big as the VP turn log, but it's not that big of a cost. Actually, the biggest cost is doing a subtraction. It's a little bit more costly. It's like 8 instructions. So 8 subtractions versus 8 64-bit subtractions versus 1 512-bit subtraction that has 8 instructions. Yeah, you're not really winning an instruction count. Anyways, okay, so we start off with a for loop. We're going 8 times over 64 bytes. I read in a 64-byte vector, and the first thing I do is I actually classify it using the vperm2 instruction. This instruction allows us to look up 64 bytes into a 128-byte table all at once in parallel. We can do this in 5 cycles. And here is a, let's say, symbolic implementation of it. The table is baked into the switch statement in this case, but it's going to be doing the same thing as what we just asked for. So we're going to have a result vector that's 64 bytes, and we're going to go over each index, 0 through 64, and we look at position I of the indices vector. We take the byte and we truncate it to a U7. Who can tell me the range of a U7?
128? Like, give me like number.
Yeah, what's the range of a U7? Like what numbers can it represent?
From 0 to 127.
There you go. So yeah, we have that here in this switched case, and we could also have implemented this with a table, but just for edification purposes, I made a switch. So the first thing we do, all of these characters here that can participate in a multi-character symbol, we map to some value between 1 and 15, or actually the important thing is that it's 0 through 15. And you can see we're missing 6 here as well, because we don't need 6. The point of this is what I actually want to do is I want to do this vectorized classification and feed it directly into a VP chef B, which I showed a minute ago. Because a VP chef B allows us to look up things within a 16-byte table. And so we really want these indices to be, to be within the 16-byte range, basically. And so we want to feed it into multiple VP chef Bs as part of doing multi-character symbol matching, because effectively we have a trie in SIMD that we're traversing. And so we're going to be doing multiple of these table lookups. So it's nice that that we can map these all to the range where we can then use this to look up in 3 different tables, which you'll see. Every other thing that we have, we map to a number that's greater than or equal to 128. And it's for the same reason. When we pass it into a VP chef B, unmodified, the semantics of that instruction is that if you pass in a number that's greater than 128, in other words, if the most significant bit is set, then it's going to zero out the result without looking it up in the table. And so using this specific classification, I can just pass this into VP chef B, and the only thing that will return any answer that's not 0 are these particular characters here. Which is pretty cool. These are the single character symbols that cannot participate in a multi-character symbol. And then we also have some other stuff. We have our @ backslash. This one right here are hashtag, $, and backtick. This is the unknown tag actually. And we have white space, quotes, apostrophe. The other thing we do is we map the alphabetic or underscore characters to a single number. We map the bad control characters to a number. And we also map the digits to a single number. And this allows us to actually use a single vector compare equal to get a bit string that tells us where each of these things in their respective category are. And so, you know, before, when we wanted to figure out where the alphabetic or underscore characters, we had a more complicated set of assembly code because it wanted to map the uppercase and lowercase characters into the same range by doing a math operation and then checking that range. And yeah, you just inherently need multiple steps. Here we can just say, tell me where the 180 bytes are in this result. We can do that in one instruction, and there you go. Okay, so first thing we want to do, we want to see where the non-ASCII characters. If there are none of them, we don't have to do anything. If there are some non-ASCII characters, it's highly unlikely. I put a branch hint there. Then we, first of all, correct our classified object that we got out of vperm2. And the reason why is because if you look at the semantics that I showed just now, we're truncating each byte of chunk to a U7. So we're just ignoring the uppermost bit, which means that we're mapping the upper 128 numbers and the lower 128 numbers to the same thing, when that's actually not what we want. And in this case, it's extremely rare to have a non-ASCII character, and so I can just hide it behind a branch like this. We could say, okay, if we have any non-ASCII, just map it to the unknown character class. In real code, you would need a @enum from int, or sorry, @int from enum. But yes, I just made it a little shorter here. Okay, so you can look it up in your UTF-8 checker. I'm not going to show how that works because I didn't even actually like do the engineering behind that. I improved it slightly, but this is actually the work from Daniel Meyer, Cindy UTF, and Cindy JSON, all that stuff. And yeah, we're passing in cursor.pointer equals source.pointer because it's valid to have this byte order mark at the start. It's just an implementation detail. The point is, if there's this particular 3-character UTF-8 thing at the start of a file, then we just convert it to new lines and pass it through the system as new lines, because that's the easiest way to do it. Otherwise, if we don't have to do a real UTF-8 parse, if it's all ASCII, but our UTF-8 checker ended in an invalid state from before, we can return there. Okay, whatever. We store the classified table lookup that we did, and here we are producing bit strings again. So I just made this v equal helper, but yeah, we produce the bit string that tells us where the carriage returns, where the new lines, where the slashes, backslashes, where the quotes, where the apostrophes, where are the ats, where are the bad controls, where are the digits, where are the white space, where the alpha or underscore, and then this one actually tells us where are all possible symbols. There might be single character symbols, might be multi-character symbols. And yeah, all of these are one instruction right here. All these, a single compare equal instruction. And then this one is less than or equal to. Okay. The other thing we want to do is we want to produce the multi-character masks. This is what I was talking about. We pass in that classified table, and that's what I'm going to show next. But yes, at the end of this for loop, we check is cursor.len less than 64. If it is, then zero out the bit strings we're not using. And I didn't mention it, but up here, I said in the real code we actually handle not unconditionally reading 64 bytes, but I didn't want to get bogged down into that. Okay, so we have get multi-character masks. This one is actually cool. We use some comp time metaprogramming to produce the table that we want to pass into VP-SHUB-B. I have this channels struct where each bit of the struct represents one of these lines down here. So right here, what we want to do is we want to look at, for all character positions in the file, we want to find something. There's going to be one character from the first string in the array of 3 elements, something from the first, something from the second, and optionally something from the third. And that's the pattern for all of these. and we can actually match all of these in parallel by putting them on different bits. When we look it up in the table, we're going to get back 8 bits. So if the first bit is set, when we check against the first character, that tells us it's in this set right here. If the second bit is set, it tells us it's in this set. And if the third bit is set, that means it's one of these. In this case, there's only one. And so if we line these up by doing a vector shift, we can just do an and this will tell us, okay, if it's in the set of things in the first set, and it's in the second set, it's in the third set, if those things align, then any combination will give you a valid operator for each of these channels, is what I call them. And so yeah, we produce the table. It's not too much fanfare here. I actually have this hash opchars because originally I wanted to do some hashing to generate it, which is why we're missing 6. But now we just do vperm2 anyway, so it doesn't matter. Okay, we have a special channel which is self. This is an interesting detail. You don't have to rigorously maintain, constraints that you do for everything else. Here we have a self channel. And so the idea with that one in particular is it's not just anything from the first set and anything from the second set. We actually want them to be the same character. And so we check that. And yeah, so we just have state without self. So we just produce the bit string of 8 bits channels, and then we just zero out the self channel. That way, when we do our shifts, you can see that we do an and with a select here, where we're going to zero out the self bit if the two don't match. And so all we're saying here is look up the classified table that we had, look it up in the second character data, tell me if that matches with the previous character looked up into the first character data. So we're just doing a shift, we're just lining it up. Very simple. And we do the same thing for triple char ends. It actually builds on double char ends right here. And so we just shift that over by 1. We pull in 1 value from the previous double char ends if this is not our first iteration through. And yeah, we line it up, we do an and, we do the same thing. We're going to zero out the self bit if the two characters are not the same. And yeah, we just hold state for the next time. And then what this will do is it will give us two vectors. We have double char ends and triple char ends. And there's going to be non-zero values in there if we found the end of a multi-character symbol that is in one of the sets that we set. And so we can just check which ones are non-zero. This will just produce a flat bit string that we can use later. Okay. So we read all the stuff from bitsters in. We check, are there any bad controls? We can return an error on that. We might want to change it so it will just make an invalid token or whatever, which is what the conventional tokenizer does right now. Anyways, we can also check it for all carriage returns. Is there a new line immediately after? That's in the language spec. The way that we do that is we just say, okay, do we have an offender, which is a non-new line or end of file, because I pass the end of files as new lines to the system, just to make it easier. Do we have a non-new line or end of file? And to its left is a carriage return. That's all this says. And yeah, if we have an offender, then we can throw an error. All right. So in the course of figuring out the boundaries of strings and comments and what have you, we need to figure out what to do about escaped characters. So here's an example. Imagine you have a ton of backslashes represented by 1s here. And we want to do this algorithm. This is actually created by John Kaiser for SUNY-JSON. It's under the Apache 2.0 license. And you can look at that pull request if you want to go see the origin of the code. And you can also read his explanation. So we start off, we create an odd bits bit string. One thing I want to say is that the bit string, we're looking at it from a left to right view. So the source file goes from left to right, and the bit string also goes from left to right in this depiction. Oftentimes we see bit strings written the other way, but when it comes to SIMD, a lot of times it makes sense to write it, let's say, backwards. So yes, so this represents the odd bits. The least significant bit is on the left. And I'm using dots to represent zeros here, so that there's more of a visual difference between a 1 and a 0. Okay, so we have some persistent state across chunks. I'm just going to say it's 0 for the first time. And yeah, we do it and not with 0. Okay, whatever. So let's just call the input is equal to this variable, potential escape. So let's start with that. I was expecting a cool animation there, but it did not happen. Okay, so we have maybe escaped. We just shift the potential escape to the left by 1, which is right visually. So this 0 is the one that was shifted in, and we should lose one value over here, but it's still there. So amazing. Okay. What are we doing? All right, we have even series. All right, we're having technical issues here. I'm going to try to add extra lines to it. Hopefully it will scroll properly. Two seconds. Okay. I wonder if maybe I touched something on the other screen because it was open. All right. Can I get over here? There we go. Okay, so we have even series, and we're going to take the OR of odd bits and maybe escaped, which looks like that. And I have it kind of color coded so you can see which bits we're merging in here. And we do a subtraction between that and potential escape. I'm not using the default operator here because we want to do a 512-bit subtraction, and LVM does not have a routine baked in for that, but I have one implemented there. So we do a subtraction, we get even series out, it looks like this. We do an XOR with the odd bits, we get this. And we do an XOR with backslashes, basically, and we get the answer. All right, so how did that work? I don't know. I didn't make this. No, actually, basically what we're doing, we do a shift in order to figure out basically where are the candidate escaped characters, right? So each one represents a backslash. What we're interested in finding out is for each character, are there an odd number of backslashes contiguously preceding it? And so, you know, I will just say, I think it's going to move it up. Oh my gosh. See, once you try to show people something, it stops working. It was totally working before. Oh my goodness. I wonder if I can hit Control Z on my presentation, maybe. Yeah, I don't know why it's doing that. Okay, well, this is the correct answer that we're looking for. And the way that we got it, yeah, it's basically, we tried to figure out where are the candidates by shifting to the left by 1, because we're looking at something that comes after a backslash. We do an OR, and we do a subtraction, we do some XOR stuff. Effectively, what we're doing is, yeah, we are flipping bits following a set of contiguous bits based on whether the contiguous bit string of ones has an even or odd number, and also whether it occurs on an even or odd bit indice. And so, yeah, it's a clever trick. I will say I don't actually fully understand it, but I don't have to because someone else figured this out. So, amazing. Okay, so we take the escaped bit string. This tells us which quotes and apostrophes are escaped by backslashes before them, or really anything. Any character could have an odd number of backslashes. So we just say where are the unescaped quotes, where are the unescaped apostrophes. It's pretty trivial to figure that logic out. Okay, so let's imagine that we have this really horrible string as input to our tokenizer, and we want to know where the boundaries between the strings and the comments and character literals. So the first thing we do is we figure out where are there 2 slashes in a row. And so all we have to do for that is we just say slashes ended with the shift right of slashes by 1. So we're just saying, where do we have a slash? And to its right, there was a slash. We also have this carry.get object, which is a nice wrapper that helps us get cross-chunk information in. If we end it on a slash and the start character is a slash, we're going to have a let's say, dummy bit there. We're going to have to correct the position of it later. But yeah, we can do an and with it shifted, but none of my animations are working. Is there an error in this or what? Oh my goodness. No errors.
I see a lot of integers.
It's a lot of integers. Oh my goodness. Well, it was working like 30 minutes ago, I swear. I don't know why. We have appearance and disappearance. That works. All right, so we're supposed to end it with this shifted to the right by 1, visually left. And we end up with this bit string here. And we do the same thing for comment bounds, same thing for line string bounds, and quote bounds. So we end up with these bit strings. What's the point? The point is, we also do a thing with that. I don't even want to go over that. All right, the point is, we produce a bit string that has all the bounds in it by ORing all 4 of these together. So this just tells us where are there quotes, where are there apostrophes, both of those have to be not escaped, where are there 2 slashes, and where are there 2 backslashes. So these are all the places where things could start. In the case of quotes and apostrophes, those also can close themselves too. So what are we doing with this? We figure out where the carriages are new lines, and then we produce this iter bit string, which is something that's not a carriage or a new line, and to its left was a carriage or new line. So what does that mean? It means we're going to place a bit on each line. So I have underscores denoting a new line here, just so it lines up. But yes, so we can actually do this work of figuring out where are the boundaries of quotes and comments, etc. We can do this for all of the lines that we can see at once. And so we produce this iter bit string, which points to the start of each line. We have a loop. We take the OR of all bounds and the carriages or new lines, and we subtract iter from that. That will give us a bit string that looks like this. And we do an and not with the all bounds, and that gets us the starts bit string. So this is the main thing here about parsing with bit manipulation, is doing this and, the subtraction, and the and not. This is a very common trick. What we just did is we actually advanced every bit of iter right here. I can scroll a little bit. Every bit of iter, we advanced it to the next bit in this bit string here, effectively. And so you can see that when you look at iter, this bit wants to grab the next one in the series of either carriage return or new line, or all bounds. So in this case, when we're looking for the start of each thing, we're going to find the first quote on each line, or the first character literal on each line, or the first comment on each line, if that's the first thing that occurs. Okay. Next, we want to interleave stuff. So what does this mean? We start off with each carriage or new line, and then we merge in the characters by subtracting this from carriages. So what we're doing is we're saying, okay, from each starting position on each line, so if there's a quote, like right here, what we want to do is we want to produce some 1 bits that go until the next new line. And then for this one, we want to say, okay, let's go until the next new line. And we want to merge in until the next new line the quote bounds for quotes. And so when we do another subtraction where we say, okay, we're going to heat seek again for each iterator is now going to match against the thing that ends it. So this one is just for quotes, but after it we have one for apostrophes. And then, of course, we started with new lines. And so if there is no close quote or close apostrophe, we will hit this new line here. And then we delete the starts, and we do the subtraction that I said. And so this will get you cur ends, which we should be able to see here, but we cannot. Amazing. So cur ends, it just matches each individual quote on each line. If it's a quote, or if we started with a comment, it will find the next new line. If we started with, anything. It will heat seek to the next thing, is the point. And then we can loop back around using these lines of code. So this technique enables you to, you have a bit string, you have some other bit string, and you want to move each iterator forward within it. That's the trick that we're using. Okay, so that solves that. Afterwards, we have some kind of open code here. We say, where does each, we get all of the starts and ends from that loop. So that was another thing that we do. We merge in, anytime we figure out where the end of things are, we merge that into the all ends bit string. Anytime we figure out where the starts are, we merge that into all starts. Most of my variables in this code are constants, except for these two in particular, and there's a couple other ones. But okay, so we do a subtraction. This will just give us the bounds of all strings, comments, line strings, apostrophe, character literals. This will just give us a bit string where it will we'll have 1 bit starting at the start of each of these, and it will have a 0 bit at the end of it. And there'll be 1 bit in between. So amazing. We revise all ends so that we don't include the carriages or new lines within it. So we say we want all ends to be ANDed with the not of carriages or new lines. So we want no carriages or new lines in all ends. And then we want to OR that with shifting all ends and the carriages or new lines to the right by 1. And so really what we're doing is we're just saying any place where we end on a new line, just move that back by 1 character. Okay, so we have an OR with these two things. Yeah, very cool. Some of this stuff is just implementation details. We do cross-chunk logic properly, and it does what it does. Okay, so we figure out where the ats, and we want to know the ones that are not inside of a string or comment, and the digits that are not inside of a string or comment, and the alphabetic or underscores that are not inside of a string or comment. What's an alphanumeric underscore? It's an alpha underscore ORed with digits. Amazing. Okay, so we have a couple of things here. We produce follows ats. This tells us what are the characters that follow an at character. What are the characters that follow a non-alphanumeric or underscore, and also a non-at. An identifier or a number start is some alphanumeric underscore, and it is following a non-at character, a non-alphanumeric underscore character. A string identifier is a quote. This is cross-chunk logic. So if you have a quote, there was an at that we ended on in the previous chunk, we handle it. Great. Is it split between chunks? We do some stuff. Amazing. Identifier or number or built-in ends right here. We figure out where are the ends or tokens. Where are the starts of our built-ins, where are the starts of our string identifiers. This will be an at followed by a quote. And then in the all starts bit string, we can delete the the quote starts that should correspond to the at followed by a quote. We can or the built-in starts and the string identifier starts and the number starts, and we can or the ends in. There you go. Okay, so one big thing we have to handle are the multi-character ends masks. This code took me like a week to write. It's only like a couple lines, most of it's comments, but it was actually pretty hard to figure this out. So what do we do first? We say the triple character ends are not inside of a string or comment, and it's the triple character ends that we started with. And these, so what we're starting with is we're starting with bit strings that tell us where are all possible ends for a bit string. So right here, we have a plus bar equals b. So we would have a bit string that tells us, okay, a 2-character end ends in this position, and a 3-character end ends in this position. So how do we handle that? Well, the simple thing for this particular case is when you have a triple character end, you can just shift it over by 1 and delete that bit in the double character end bit string. So it's a very simple rule. If we have a 2-character end and a valid 3-character end right next to each other, we want to go with the 3-character end. Okay. I don't want to skip over the comments. Okay, so the other thing we want to do, we're going to set S to be double char ends or triple char ends. Here's the idea. If we have some difficult overlapping set of characters, like A equals greater than equals B, we want to, this right here is a valid 2-character symbol with this. So we could have the double greater than, this would be your right shift, okay? And we also have equal greater than, and this is going to be your arrow symbol, right? We could use it in a switch statement. So what we don't want is we don't want to be matching the same character in 2 different tokens. And so what we want is we want to emulate the behavior we would have had if we went 1 by 1, which is greedily get the longest token you can, and then after that, keep doing it. So what do we do? We set ends to be 0, and we say, we have some carried state. Okay. What does this do? I don't know. It does some things. The point is, you have all these rules, and you want to delete this stuff. And it was very hard for me to come up with this, so if you have your own project where you're doing this, just steal my code. It works, and I commented how it works. And we have a loop here that we might need to run if we have a really insane string of operators. But in general, we can actually just do this over a single iteration, because what this is actually going to do is we're going to find like spaces between symbols. If they're like, if you have multi-character symbols that are spaced out, we can parse those all in parallel. But if they're right next to each other, it's more complicated, and we might have to do this loop several times. If they're far apart, like they would be in normal Zig formatted code, then we can just do one trip through the loop, and we're always going to break right there. Okay. And then, we say the double char ends at the end of the day. The 3-character sequence take precedence over the 2-character sequences, so we delete stuff there. And we take the ends, we XOR with double char ends final, because double char ends final is a subset of ends, and so we're just saying, give us the other subset. Amazing. That function right there, that's my contribution right there. This was actually super hard to come up with. Like the logic, when you actually go over it, it makes sense why it is this way. But when you write an algorithm like this, it's really like reverse engineering logic. And I don't know. That's always difficult to do. When I wrote that dynamic score decompose try paper, when I wrote the algorithm for modifying it dynamically, I got it wrong like the first 3 times, and it made sense at the end, like the result you end up with. But getting there is always just very difficult. Okay. So what are we doing? We have the double character ends inside of a bit string, triple character ends inside of a bit string, and we just delete the ones that are inside the single character end bit string that couldn't possibly be it. So we're just saying, take the possible 1 character symbols that might be in a string or comment, and it with the characters that are not inside of a string or comment, and then and it with the not of these things. So all of the things that are accounted for by double character ends and triple character ends, delete it. And so now we have exclusive single character ends, double character ends, and 3 character ends. Amazing. Yeah, pretty much what it says. We're just putting this stuff together, and we do some cross-chunk handling. And we put it in all starts, we put it in all ends. We also have invalids. All right. I feel good. This is the last bit manipulation thing. We have invalids, and yeah, what are the invalid characters? It's a bad control, or it's something that's not inside of the rest of that expression. So inside of our all starts and all ends, we have a bit string that tells us where each token starts and ends. If it's not in there, that's bad. We also OR it with all ends because the subtraction there gives us an exclusive range. And so yeah, it should be between an all start and all end. It could also be white space because we don't tokenize white space normally, so we can just OR that in. And yeah, anything that's not a white space and anything that's not a token, anything that's a bad control character, that's bad. And so we account for that. We can admit it as an invalid token. Amazing. So I have a conclusion here. I want to show a little bit more code, which I didn't put in the slides, which is right here. Oh, yeah. Oh, nope. It's actually very hard.
Quick side question while you're doing
Yeah.
that. Or equal, is that saturating or is that and equal?
Or equal is not saturating because it's not arithmetic. It's just syntactic sugar for saying, if I say A or equal B, I'm just saying, or wait, yeah, it's just syntactic sugar. I'm just saying A equals A or B. That's it. Can I, why are we doing this? Just go over there, you guys.
Also, the way you did that is different than how you explained your approach to that. I thought you had done the subtraction and you were off. You did and combine everything together.
Okay. Well, let me try one more thing. Might be because I'm full screen or something. Oh yeah, let's do this. Okay. Maybe? Maybe? Somewhere? Oh, there we go. Let's go. Okay, so the only other thing I didn't include, we have 3 phases of this loop. The first phase of the loop was producing the bit string. The second phase is we do our analysis on the bit string. We try to do everything in parallel that we can, and I still have some print debugging in there. I actually just finished this, so I didn't delete everything. And there is one more piece of analysis that we do in phase 2, which is we do some things for keyword handling and making sure that works out. All right, point of the story is phase 3 is where it all comes together. We have another loop that we do 8 times. We go over each chunk again. We read in the classified chunk again. And what's super cool is the classified chunk is actually pretty close to the correct answer that we want for our kinds vector. And the reason is because I just define the answer that we get out of here to be the correct answer. Amazing. So, we're looking for a couple things. Identifiers, we want to say it's an identifier. And so what I do is I make it so the alphabetic or underscore byte that I get out from the classifier that I use to produce the bit string that tells me where the alphabetic or underscore character is. That byte that I got, I think it was 180, I just say 180 tells me it's an identifier. So that's already in the correct position. Ditto for numbers. There's a byte corresponding to the start of each token that is a number that says it's a number. Amazing. For @ by default, I think by default it's a built-in, but we override built-ins anyways. We also override the string identifier if it's a @ string, whatever. And then, we also override the comments because by default, a slash, the kind of it is going to be division. And so if there are 2 slashes, we're going to overwrite this kind and say it's a comment. Unless it's inside of a character literal like this. But even if it is, we use vector compression to extract only the kinds that we're interested in. So yeah, we do some selects here to produce the correct kinds. We do this bits to indices function. I put in a parameter where you can have it start at 1, but I end up not using that. But this is just doing a vector compression. And so we're just saying, we produced 512 bits of starts and ends for each token. We get the indices, for each 64-bit chunk. And then, we get it for all the starts, all the ends, and we also figure out where do all the multi-character symbols end. And for multi-character symbols, we do some things. Primarily, this get multi-char kinds function. And what we're doing here is interesting. One, we actually already know that all of the multi-characters that we have in our bit strings at this point, they're valid multi-characters. And they're non-overlapping, that's all good. And so really all we have to do here is just do a little bit of cleanup. We have an adjustment vector here. And so what we're doing here is we're making a vector that we can use to read in each multi-character symbol into a 4-byte chunk of a vector. And so we're doing an adjustment vec here because we might have, the cursor is really strange. We might have a multi-character symbol that goes across 2 chunks. And so the point is we're going to do some subtraction to handle that. And then we do the vperm2, so we get each of them into 4-byte chunks of a vector, and we hash them, and we do more hashing right here, and this hash value that we get out is the correct tag, just by definition of how I organize the tags. And what's cool about this, you don't have to go look up the hash in a table and say, does this actually match the one I expected? Because we already know it matches the one we expected. This is a perfect hash function. It perfectly matches, it perfectly hashes each multi-character symbol to a unique number right there. All right. The other thing we do, we take the kinds and we use a vector expansion. It's just the opposite of a compression. We have a packed set of kinds and we spread it out to the places where it's supposed to go. For keywords, we do a similar thing right here. We hash it by taking the first 2 characters and the last 2 characters, and we handle the case where it goes across chunks. we figure out what's the length by subtracting the end from the start. In this case, we add 2. It makes sense if you think about it because we're actually taking 2 characters at once rather than typically you'd have 1. So yeah, we figure out where the first 2 characters, where the last 2 characters. We're using vperm to line these up. And so you're going to have first 2 characters, last 2 characters. First 2 characters, last 2 characters. And we hash it. And we look it up in this table here. Keyword slices raw. Can I go to definition or what? Oh, it's because the hover thing doesn't work. Okay. So what is this? Let's go to unpadded keywords. Okay. So I have a keyword buffer, and this densely holds all the keywords that are in here. And so what I do is I just have a table that maps between the hash and the index in this buffer, which is 256 bytes. It's less than 256 bytes. So it fits into 4 vectors, which means I can just load all 4 of these into vectors, and then I can load the lookups based on the hash into vectors. And then I just pull the data from there. And let's go back to definition. And yeah, so I look up where does each one start and what's the length in the buffer, and then I grab 8 bytes from my source file, 8 bytes from the buffer, and I compare the first 8 bytes, and I have a loop here. We're going to do it twice. So we look at the first 8 bytes and the second 8 bytes. If we do an AND to see if both of the 8 bytes matched, and we interlace the length of the identifier after the identifier. So if we have if, for example, it's going to be if 2222222 until we run out for 16 bytes. And if we have try, it's going to be try 33333. So we do that when we pull it from the buffer, and we do that when we pull it from the source file, and that makes it so that we never incorrectly match anything. So anyways, we concatenate the answers, we do a vector expand on the things that we found, and yeah, we get the keyword data. After that, all we got to do is compress the kinds according to the all starts bit string, and this gives us up to 64 tokens with 64 kinds. And then we do a similar thing for the extents. Yeah, we're pulling out the first 8 different from the first 56 because of cross-chunk handling logic. But yeah, then we go forward by the pot count of however many bits there were in all starts. So that means how many tokens started. And then we go forward in our cur kind and cur extents pointers, which is where we're writing out data. And after that, we're done. This is all garbage stuff. We handle some of the cross-chunk stuff. We save the slashes bit string. We're going to want the uppermost bit in the next iteration. Backslashes bit string, same thing. We just want to store the uppermost bit of each of these things so that we can access it in separate, in subsequent iterations. Okay, so what do? We unlocked a new level of parallelism. Amazing. We are able to tokenize a whole chunk of data at once rather than individual bytes or individual tokens. Now the amount of work that we're doing is roughly proportional to the number of 64 or 512 byte chunks. This is nice because we have significantly more parallelism available to us within a single thread. We have significantly more instruction level parallelism. We have significantly more data level parallelism by going wider and using SIMD instructions rather than general purpose instructions. You know, we have things like VP turn log Q, which we can do 16 times more work using that. I sent this to someone with a Zen 5 desktop, and they showed me a number they could get 2.5 gigabytes per second using my code. This is compared to my old 64 bytes at a time version, which could only get 1.4 gigabytes per second. I don't know how much I can guarantee 2.5 because when I actually like fixed the code all the way, there was a performance regression where it actually is closer to this, but there's still some more like little assembly level improvements that I could make, and maybe I just tripped over the wrong thing in LVM and made it roughly equal in speed. But even if it is roughly equal in speed, what's exciting about this work and all these features is that this is something that is actually like, you can have a better CPU that runs this better, or you could actually port this to a GPU because actually the entire logic could be branchless. We only have branches for performance reasons. Yeah, we could actually just unroll the loops where we could, and yeah, we would have no branches except for the outer loop. That is totally feasible for this implementation, and it's thanks to doing everything in SIMD and using primitives with inherent parallelism available. So hopefully this helps out the future, helps out very powerful computers going forward, and yeah, that's all I have for today.
I personally want to congratulate you on a record speed.
Yeah.
I don't think anybody expected you to be able to move through that many slides in so little time. So
Yeah.
Congratulations.
Thank you.
And while we're being a little sarcastic and snarky, I want to highlight a comment by Tech Buddy who said, I have no idea how this thing works, 100%. This is too much SIMD happening.
I love Tech Buddy.
Okay, and then we got a couple of other questions here. Andrew Code says, awesome stuff, Niles. I'm interpreting that as a grateful thank you. Back to the hash function. When you say you chose a hash function that matches your option values, do you mean you pre-ran inputs and then mapped them to the values you wanted after? I think he's asking, is this a generated perfect hash? Right?
So the perfect hash, I did write scripts to come up with those. I still have them. And it's not that sophisticated. It just tries a couple different things.
By a couple, you mean like a few million?
Yeah, I mean, there's a loop. But what I mean by a couple is like there's a couple different strategies. So I'm like, let's try doing a shift left first and then doing a multiplier, so just a different like permutations of operations, and then you just kind of brute force the numbers, and that would be like millions of things or billions of things, and I just let it run for 20 seconds, 30 seconds, and found a couple of hash functions to use. And then, just kind of selectively planned out the tag, the kind space for each token that way. A lot of the perfect hash functions that I found, they fit into a U6 or sometimes a U7. And so, I just made sure that it's like the keywords are going to be up here and the multi-character symbols are going to be down here. And just kind of make sure that there's space for everything. It's probably the process you would imagine if you had to do it yourself. I don't have any like magical god tier math abilities to just divine a hash function out of nowhere.
Are you sure? Because we're on part 4 of hyper-optimizing for the Zip Parser. You may have misestimated.
Well, it's just I just ran a program and I just mapped out the space in a way that I can computationally easily get to the output I want.
Cool. So, is this it?
This is it. I might do a couple more animations and like post those elsewhere, but this is actually like it works now. I fixed the cross chunk logic, which I left sitting there for a very long time. But yeah, I actually fixed it and it actually works now.
So when's it going into mainline?
We'll see. I'll clean it up and make my pitch, and we'll see how many people prefer this to going one character at a time in a finite state machine. and then I'll finish my parser stuff too, and we'll get that out too.
Yeah, so TechBuddy feels like we were lied to because we don't have the parser in the main lines yet, so.
Yeah, the parser. Let me say this: when I first made it, I didn't even like fully finish the tokenizer, and I was trying to do too many radically different things at once, and so I had to scale back and say like, let's just do one thing that's crazy at once, and yeah, for the parser, it's like I basically bit off more than I can chew, is what I was saying.
Nobody believes that.
Yeah, so yeah, the parser, I will do it. It will come, and yeah, maybe that'll be my talk in 6 months or something, when it's my turn next.
You're the Chuck Norris of parsers. You don't bite off more than you can chew. The chew is more than can bite you.
Yeah, the chew is more than can be bit off.
And Andrew Code also astutely points out that none of us have seen you and Bruce Wayne in the same room before, which leaves some question. I don't know,
Yeah.
maybe we shouldn't be talking about this on the internet where everybody can.
Yeah, let's talk about that offline, once we turn the stream off.
Okay, we'll take that one offline. Okay.
Yeah.
Any other comments, questions?
Okay, that series of 256-bit strings that you use, are you manually writing that from the list of keywords it has? Or are you doing that
Okay, so that was generated.
to be as small as possible to fit within those constraints?
Well, AJ, what do you have to say about that?
What do I have to say about adders?
What it takes to-
test for
What it takes to generate this
So
as small as possible.
it's looking for words that start and end with the same letters.
No, I understand that. I just wanted to double check whether or not you.
Yeah, it's equivalent. The algorithm for this is equivalent to the traveling salesman problem. So
Yeah.
it's basically infeasible to find the perfect answer that is the most space efficient it could be. And so this was just using a heuristic algorithm that I found on like one of those really dumb sites where they have JavaScript, and I just like copied the JavaScript, didn't really look at what it does, pasted in the keyword list, and it spat that out, and I'm like, great. That was the process for that.
Okay.
I think that you could exhaustively for this number of words. No, maybe you couldn't. Because after
That's too many, yeah.
about like 10 or 11 words, it starts to reach where it would take hours.
Yeah, because it would be like 49 factorial, because it's like 49.
Okay, yeah.
So yeah, that's basically a bajillion quadrillion.
Yeah, because it's like up to 7, you can do it in a matter of milliseconds, and then like you hit 8, 9, 10,
Yeah.
11, and then like by 12, you can't do it anymore. Or I think you still can, but it's like,
It'll take you forever, yeah.
yeah. Because I did I did a BOGO sort one time.
There you go.
I was really surprised. I optimized it, and I found that by making the random distribution more even, it was significantly faster, even though it was randomizing the list every single time. It was an order or 2 orders of, it was at least 1 order of magnitude faster to use a more even random distribution to randomly sort them.
There you go.
Yeah. Using a biased random algorithm
Yeah.
resulted in significantly worse times.
Okay, one more question. Why do you use ArrayList unmanaged versus ArrayList?
So most experienced iguanas actually prefer the unmanaged variants of these things, and the managed versions are actually going to be deleted from the standard library. So the reason why I do it, actually even before that, is because I agree with the idea of it. I can just pass in the same allocator every time, and it's really no trouble for my code. Yeah, I'm not like losing track of what allocator I'm using. So for me, like solving the problem of holding a reference to the right one is not really helpful. And so I just don't, I just don't want to store the allocator in there. Maybe LLVM would actually just take it out for me, but yeah, in general, I just use the unmanaged version of any data type.
Got it. I lied, I still have one more question.
Go ahead.
When you were wiping out the end indices based on like whether or not they're double quotes or why not? Why did you? Because it seems like you built up to the list of every. If I understood this correctly, you built up to the list of every position that couldn't possibly have it, and then you removed it from your start and indices, so that you have valid start and indices and then.
You're talking about the invalids bit stream?
Yeah.
Yeah, so I'm saying anything that's not inside of any other token, which is this,
Yes.
and then anything that's not a white space, because we're not tracking white space in tokens.
No, I get this part.
Yeah.
But like in my head, how I would have coded this is the inverse of this. Instead of trying to find what's invalid, I would have tried to find what's all the valid cases and do this in reverse instead. So I wanted to ask why you chose it this way.
Yeah,
'Cause wouldn't
I am
have
doing
thought-
it in reverse. I'm first figuring out where does every possible token start and end, and then using that I figure out invalids. This is at the very end of everything else. So I am doing it in the
Oh,
order
okay.
you would think.
Then I just misunderstood.
Yeah, yeah. This is just at the very end. This is after all other starts and ends have been exhausted, where I tried to find all possible tokens that there could be, and then if it can't fit into anything, like if I just have like a hanging at or something, this will get picked up as an invalid, and it will be emitted as an invalid token. Which, yeah, that's one thing about this that's, I guess, to do. I could move the returned errors. I could move that over to invalid tokens being emitted instead. Oh yeah, a cool thing that's in here but wasn't in the slides. This is the version of the code that you would need if you did not have the guarantee that Zig has, which is that you can look at each line independently to find the comments and the quotes and the line strings and the apostrophe character literals. So yeah, if you're on a different programming language and you want to steal this, you can. You might have to modify it because there's slightly different things in slightly different languages. But yeah, in general, if you can only go one at a time, for example, in C you have these multi-character comments. It's more complicated to handle. There you go.
So what are your thoughts on multi-line comments?
I really like what Zig is trying to do with that. This particular piece of code is actually only slightly slower than the more optimized version here, because there are other costs associated with this. So yeah, I mean, I like it. It's nice that you can jump to the middle of a file and you could potentially parallelize that way, which is something I haven't done here, nor do I think I necessarily need to, because we can already go like 5 times faster than the conventional tokenizer. But yeah, the nice thing about it is you can jump to the middle of the file, go to the next new line, and you know that you're in a clean state. And you can tokenize that separately, and then you could potentially mem copy that over to the first thread that's parsing the first half. So you could do stuff like that. Do I think it actually helps in practice? Not really. It's one of those things where I think it feels nice to look at. I mean, I like it better than JavaScript comments, but it also multi-line comments I think are not bad. They don't really bother me in any way. So
I'm convinced that not having multi-line comments is the wiser choice. It's the more prudent choice.
Yeah, I mean,
I
I
thought it
agree,
too
but
much,
I just think it's slight. I feel like it's a slight difference.
Well, when you think about all the code tools though, like,
Yeah,
if
most
you
of them
if
are
you use
regex.
Vim or VS
Yeah.
Code or, yeah, a lot of them are regex, and so a lot of times when they are looking at comments, because like, okay, there'll be your parser that's like, okay, this is a absolute 100%, this is a Zig code syntax aware thing. And then there's like, here's the generic one that will work most of the time for most languages, because most languages have similar constructs, so we'll just consider double slash, triple slash, pound sign, starts with a semicolon, starts with a quote, something like that, you know, like we'll just consider all those comments. So anyway, I do like the simplicity of it.
I really like ghosty as a term.
I use it. I wouldn't say that I'm enough of a terminal master to notice a big difference from other ones. It does feel pretty speedy. I mean, yeah, I like it, but yeah.
Have you used a terminal that you thought was slow?
Yes, Windows terminal. Pissing me off. So
Like, I don't know. I'm using VS Code right now, so like anything
That's not a terminal.
well, I mean there is an integrated terminal in here.
That doesn't count. It's JavaScript. It's HTML. That doesn't count.
The thing I was going to say is that this is not the speediest thing anyway, and so for me to like talk about terminal speed, I'm like, well, I'm already using VS Code, so
Wait, this is VS Code?
yeah, this is VS Code right here.
Oh,
And
wait,
yeah,
so what was Ghosty then?
Ghosty.
Oh, wait, hold on. Oh, okay, I missed. I thought that was Ghosty because he just mentioned Ghosty. I didn't realize.
There you go. This is Ghosty.
Oh, okay. Great.
So
Awesome.
I don't know. You can cat a super long file and it'll be super fast.
Well, that's great. I love it when I can count my binary files
Yeah.
so fast.
Super fast. Blazingly fast.
That's excellent. Okay, anything else?
No, I'm done.
Okay, well then I'm going to cut off the stream. So all you suckers on the stream had your snarky, terrible things to say, then didn't get to say them. Too bad. And the rest of you, don't come back because we have no need for polite company. We only want the snarky, fun people. Oh, one last question. Okay, summarize in very little words, in very short sentence,
Okay.
what is the overarching idea of this parser
Yeah.
that you've now spent 4 presentations and at least 12 hours in
Yeah.
presentation time on?
The basic idea is what I was showing before. If I go back. Sorry, it's really hard to control that.
And how many hundreds of hours have you put into this?
Less than you might think, actually. I've put
So
it
modest.
off a
So
while.
modest.
Just the website looks like a big headache, and then you have all this integrated stuff. With all
Okay, the basic idea, right? And I have this on the blog, and I went over this more in my previous talk.
No.
We're
None of
doing the
this.
analysis.
Small words. Small words.
Small words.
No, take
Okay.
that away. Take that away right now. Close that out. Just in small words.
Small words. Here's
What's
the
the
basic
big idea?
The big idea is you can, in SIMD, produce bit strings. And those bit strings are sufficient to do all the analysis you might be interested in. And you can actually do everything in parallel except for the things that I explicitly mentioned, like strings, comments, line strings. Obviously there's a hierarchy there. You have to figure out the boundaries between those first. But after you do, you can do all of the cross-character analysis in parallel. You can say, where do I have an @ followed by a string? Where do I have an alphanumeric underscore that came after a non-alphanumeric underscore? And so what you do is you produce 2-bit strings, all starts, all ends, and it just marks. Each 1 bit in there corresponds to a start of a token, and each 1 bit in the all ends corresponds to the end of a token. Using vector compression, I can move the data that's interesting for those tokens such that they're aligned, whether it's the indices So I can figure out the length if I want to by subtracting. Or if it's the tag, I can compress and take all the tags that I'm interested in.
No, he says, I meant the parse tree.
Oh, the parse tree. That's that's a different 2-hour talk. But
No tree at all?
all right, look. All right,
Okay.
I'll just tell you this. The basic idea of the parse tree, you're using a modified shunting yard algorithm to rearrange the bytes, which represent the kinds of each token. We divide it into 2 categories. If you want to go on my website, the second half of this talk, these slides, and these slides have some information on this. But the basic idea is you take the kinds. You separate out the operands and the operators because it turns out that you can do what is equivalent to what everyone else does for parsing, where they do a standard recursive descent algorithm. You can do this with a modified shunting yard algorithm exclusively on the kind bytes of the operators and a bit string that tells you how to interleave the operators with the operands. And so what you do is you kind of do a shunting yard algorithm for that. And what you end up with is basically you have a linked list of these bytes and bit strings that then can be interleaved with the operators and operands, which allows you to produce an implicit tree, which is equivalent to the abstract syntax tree that you would typically produce. Basically, it's like prefix notation or Polish notation, or reverse Polish. I always forget which is which, but it's prefix notation basically. Instead of 2 plus 5, you have plus 2, 5. Guess what? Anytime you produce an abstract syntax tree, they're doing that same reordering. There are specific projects that choose to do it a different way, where they basically produce a postfix format and they consume it in postfix, but everyone else is implicitly doing a prefix transformation, and you see that when you traverse the abstract syntax tree, you're traversing it in pre-order. What's interesting is that when you move something from in order, and some of the operators are going to be pre-order and post-order, when you move it all to pre-order, it's trivial to move it back to the order it was originally in the file. And so when you do the reordering of just the bytes, it's very easy to go the other way and take the original data, let's say, of the token, let's say the start and end that got left behind when you rearranged the bytes. You can go grab that because you can perfectly reproduce the order that something was in the file when you have a pre-order version of it. When you represent it as pre-order, every single token has a fixed arity, which means that you can represent the tree structure without any pointers. This imposes a limitation that you can only traverse the structure in the specific order that it occurs in the array by adding 1 to your index each time. However, for abstract syntax trees and basically all applications I've ever seen of those structures, you're always traversing the whole thing, and you're always traversing basically in pre-order, in the same order every time. Depth first traversals they're always the same. And so for me, there's no point in having a complicated pointer-based structure where you're hopping through memory, when actually what you can just do is add 1 to get the left child, and just recursively unwrap each child's by adding 1 to get the left, it's basically like just take the idea of prefix notation and apply it to abstract syntax tree. You can actually generalize this. There are a couple of, let's say, tricks, idea tricks. A semicolon, you can make it like a prefix operate, or move it to the front and say, this is my statement node, okay? The semicolon tells you it's a statement, go figure. When you see var or consts, some of these things you internally classify from the perspective of the algorithm as a unary prefix operator, just so it can pass through in basically the order that you expect. Then the idea is that when you consume it, rather than having an abstract syntax tree which extracted out the information you're interested in, it's actually just all in line in C2 directly when you consume it. And so you can just, you can basically, you can optimistically consume it at the point where you need it. There you go.
Okay, so he's relented and now decided that it's best if you just buy him a flight to come out and see you.
Okay.
That's not what he said, but he'll contact you on Discord so that he can have a 3-hour long call with you.
Yeah, I will say it is kind of, it's a concept that hasn't like been done that much. I don't know if it has been done, but it's hard for me to just say in words. I did try to draw more pictures with my last talk on that particular subject. And yeah, if you didn't get it, maybe I'll just have to produce the code and you can look at the code. It might be easier that way. It's hard to describe.
All right. Well, let's give 2 more rounds of applause. Once for this presentation again. And then a much bigger one for the completion of the series. Congratulations, adios, and good night.
You got a great byline.